My name is Kurtis Bowman. I'm the chair of UALink. I'm also an AMD employee where I work in the architecture and strategy team. Going to talk to you today about UALink, and thank you, Jay, for teeing it up. Here, let me talk to you a little bit about the inflection point we're at. Right, one is AI clusters. They are growing from racks to campus scale. So you heard that in the previous pitch, right? Which was we're going to scale up, scale out, scale across. Accelerators are growing exponentially. So truly straight up, and all you got to do is look at an NVIDIA quarterly announcement, and you realize just how fast they're growing. The memory bandwidth, it's what we used to think of as the clock speed, right? We used to talk about megahertz and then gigahertz on the processors. That's not the interesting thing in data centers today. It's really about the memory bandwidth and what that means to you, and that's what's going to drive your performance. And finally, the capacity. You're going to see that the models have grown way beyond what can fit in a single GPU or a group of 4 or a group of 8. And that's why we're growing to see, the NVL 72. That's not going to be enough. We need to get to 128. We need to get to 256. Those are going to be the key areas that we'll be driving and we're going to see over the next 3 to 5 years. And then finally, your interconnect. It really is the strategic piece in your data center. If you don't take anything else away from this whole presentation, it's that one bullet that you need to think about as you're thinking about the planning you need to do for your data center. Now, I'm not going to drain this slide, but it'll be in the presentation. The big thing you got to think about is, why do I need scale up versus scale out? They're two very different solution sets. In the scale up area, you're really trying to maximize for performance because you're creating one GPU out of multiple. And to do that, you've got to make it look like one GPU to software. You're not trying to service the hardware. You're trying to service the software developers. And you need to be able to work into those frameworks. The memory model, it's got to be true memory access. It's got to be reads and writes. It's got to be the load stores. If it's not that, you're spending way too much time in an RDMA loop to make it useful in a scale-up environment. Scale out can tolerate that. Your latency sensitivity is another one that's really important to you because it's what defines how fast you move. And in particular, your tail latency is what you want to look at because it's about who comes in last that is going to define how fast you can move forward. So if I've got a long tail latency, I'm in trouble. I've got a bunch of very expensive GPU cores twiddling their thumbs waiting for that last guy to finally finish crossing the finish line. And then, why is that important? Well, for training, bandwidth is the key to your performance. You've got to have high-speed links. Many technologies will solve that problem for you. Inference. This is going to be 80% of what goes on in AI over the next 3 to 5 years. Ultra-low latency is what's going to define your performance. If you don't have that low latency, including that low tail latency, you will not meet your expectations. A little bit more, just to kind of put it in a pictorial form. Scale up, or the easiest way to think about it, how do I make one giant GPU? The picture kind of shows 4 GPUs connected together in the old school way, but it's going to that switched architecture that we're talking about. Again, you think about load store, you think about UALink as the way to create this pod of accelerators. Then when you go to scale out, right, it's really about connecting all those pods so that I want to be able to connect many, many of those giant GPUs. And what you're going to see is it's typically done through DMA, which is something that Ethernet is very good at, and packetized I/O, again, something that Ethernet's good at. That's where Ethernet fits very, very well, exactly to Jay's point earlier. But you've got to remember your typical latencies. Even in the TH6, it's measured in microseconds, not nanoseconds. That's why you need a UALink. Now, we get to some of the points that Jay made. You need open. You got to have it, right? UALink is 115 members. it crosses from IP vendors to silicon vendors to end users, all coming in to make sure that we're doing the right thing for an open environment. We want to make sure that the scale-up fabric is purpose-built so that it really does meet the same performance that NVLink is going to meet. This is the open version of NVLink. And then it's complementary, right? When you start to think about it, and I'll show it on the next slide. When you think about one die, you have very high-speed interconnects within the die. Then things like UCIe, they help to define what the chiplet interconnect is. CXL and PCIe are playing there. UALink makes its needs known for the scale-up environment. And then Ethernet and InfiniBand are there for your scale-out space. Things that are critical. Obviously, we've talked about performance, an important piece of what we do. Reliability is another key piece that you have to have. If you don't have that end-to-end data protection, your data is exposed. If you don't have the error detection and flit replay at the link layer, that means your tail latencies go way up, right? So if you have to go all the way up your Ethernet stack before you can realize you have to replay, that is going to finish far behind everybody else. In UALink, it's done at the link layer. And so it's a very fast retry. Your tail latencies, even on an error, are kept low. And then fault isolation and monitoring. If something fails, you've got to easily be able to tell what's failed so you can go fix it. Same thing with security, right? The one thing we've all learned is there's two types of companies. There's those that have been hacked and those that don't know they've been hacked. And that's about it. You've got to make sure you've got security there so that as people get in, you do have protected data and you can allow multi-tenancy safely, right? So you've got the isolation of the pod, you've got encrypted links, you've got authorizations for those, authentications for those, and then you also make sure that you've got controlled access. UALink brings all that to the table. When you think about open, why does it matter? Vendor lock-in is number one, right? Anybody, again, if you looked at the NVIDIA quarterly announcements or quarterly earnings, they got you locked in, right? And they're making 80 points of margin on us. That's just not acceptable. We need to have supply chain solutions where we can actually go out and choose vendors and they can be interoperable, with what we're doing. Cost and power constraints is another thing that comes in here, right? If you're the only game in town, you don't have to be as innovative. You don't have to be as good at costs. And so you want to be able to leverage the power of a consortium to come up with those innovative solutions and also, be able to use multiple vendors in what you're doing. That's where this comes in. So you can see the board of directors. It's really the who's who of the industry. It includes the cloud providers, the silicon providers, the IP providers, right, are all there. And then we've got a great sampling of our members that are part of this. When we talked about the ecosystem, what makes this work? It's really simple. You get the IP guys like Synopsys and Cadence. They make the piece of the puzzle that makes it very easy to design into silicon. Then you get the silicon providers. These are the switch providers and the accelerator providers. So folks like Marvell are creating a UALink switch. Folks like Astera Labs are creating that switch. Upscale AI is creating a switch, right? So that's underway. Being an AMD employee, I'll start with us. We have on our roadmap to have UALink in 27. There are other vendors working that same time frame that people like AWS have said they're doing a UALink-based solution. The folks at Meta have been very supportive of this, and we see them coming in with a solution that might be in this space. Intel is president of the board, so we have a strong feeling that they might be doing something in this space. What you're seeing is anybody that's creating an accelerator is doing something with UALink. And then finally, to be able to make sure it works across all the vendors, you need to make sure your test and measurement guys are there. That way you can do compatibility testing. And we've got folks like Keysight and Teledyne LaCroix doing that testing equipment for us. We'll quickly get into the advantages. So, I said bandwidth is a key piece, very important. You can see that 800 gigabits per second, right? So that's the port. You can break that down into just 1-800, 2 400s, or 4 200s, or 4 100s. No, excuse me, I've got that one. 2 400s, 4 200s. There we go. Get my mouth right. And because we do the direct load store, what we see is we can connect up to 1,000 GPUs together, with a switched environment, allowing these accelerators to share that HBM memory and do it in a very low latency, high bandwidth way. When you start to look at what does that mean, it's an accelerator domain. You probably see 4, maybe 8 accelerators in a box. You see multiple switch boxes that come together, and then more accelerators in those different boxes, and that's how you can get up to the 1024 accelerators. When you think about performance, we've talked about high bandwidth, low latency. Easiest way to remember it is it's the raw bandwidth of Ethernet with the latency and the predictability of PCIe. When you start to look at how efficient the design is, we get about 93% efficient use of the bus. If you compare that to something like Ethernet, they're in the 60 to 80% range, depending on the size of the packet. Because UALink has one packet size, we're very efficient inside the bus. Significant die size, and by decreasing the die size, because we don't have to have the big replay buffers, we also reduce the power that's needed. And so when you start to think about how many GPUs you're going to be deploying and how many of these switches you're going to be deploying in your data center, small fractions of power savings for each of these ports, and we're talking about 72, 128, 256 ports per GPU, you start to see this is where the savings occurs, and this is one of the key reasons you're going to want to look at UALink. Obviously, it's an open standard that we talked about, and it does leverage that Ethernet layer. And so all the cables that you're currently using, all the connectors, the retimers, the management software, all understand that layer. It can help you. You don't have to reimagine anything. You can use the same supply chain you've been using. Now, when we look at a roadmap, 1.0 was announced last year in April. And we followed it up with a 1.1 and also included some lower speed connections for inside the box. 2.0 will be coming out here, about 2 weeks? I'm looking at our marketing guy. But they'll be coming out in 2 weeks. Biggest thing we include is collectives in that new setup, or what you think of as INC, in-network computing. That means that you're able to offload your bus because the switch can do some of the work. And so you end up with about half the traffic on your bus that you would. And depending on the workload, you're going to see a 15 to 20% increase in your performance just by adding INC. We're also doing a few things to our protocol layer, or our physical layer, so we've got that. We've added a management spec. We've got a compliance spec coming out shortly, and then we've also got a chiplet spec. So you're going to see all of that come out the very first part of April. Now, what does it mean when you talk about a roadmap? You got to remember, UALink is a consortium. Our product is a specification. So 1.0 comes out. We get people to start doing those designs for switches. Those are, from a 2025 spec, you're going to see parts coming out in late this year, early next year. Same thing with accelerators. When you see, the 2.0 spec that we showed on the previous slide, that means you're going to have stuff coming out roughly a year later again, so late 27, early 28. And then as we do the 3.0 that was on the following slide, you're going to see that stuff coming out another year. So, when you look at a consortium's roadmap, it's not quite the same as looking at a vendor roadmap, because we're not making the final products, we're making the spec to make sure these can all work together. So that's why I've put this out to give a better idea of when you're going to see stuff in the market. And the nice thing is these 1.0 will be out there later this year. You'll be able to actually do the measurements and see the performance relative to NVLink. So to sum it up, we believe that UALink is the right communication method for doing the scale-up networking. We think that it's for lots of reasons. One, it's very efficient bus, it's low cost, and it scales to the needs of the scale-up applications. The low latency, high bandwidth is the critical piece that will give you the performance you're looking for in your data centers. If you want, the spec is available to anybody. You don't have to be a member. You just go out to ualink.org and download the spec. You can read through it. It's not a night reading thing, right? It's about 300 and some odd pages. So you're going to spend a little time looking at it. But then you can compare that to things like eSun, who just recently launched their 1.0 spec, and you can look and see what the differences are and make those conclusions yourself. You can also, join in and be part of the fun by adding this in. And then finally, this just kind of highlights all the advantages you see with UALink. You got the high bandwidth, the low cost, the high efficiency, low power, ultra low latency, many, many members. The spec is complete, the IP is available, and we've got the switches and the GPUs are in design. So it's coming. It'll be here end of this year. And with that, I'll open it up for questions.
When you're looking at the differences and advantages, I think you said that the fixed header, having a fixed size was an advantage. Can you explain more about, what you mean by that?
Yeah, so there's a, fixed packet size, and it's set up at 64 bytes. And so you always know that your size going down the wire is going to be 64 bytes. And by doing so, I don't have to, I don't end up stuck behind a great big packet. When you look at Ethernet, it can be multiple packet sizes from 16 bytes to jumbo frames. If you get stuck behind a jumbo frame, then you're slowing things down, right? Because it's got to clear before you can actually get your first byte on the line. And so, when you look at moving data, one of the things that we found is you've got to move it in those small chunks. And you have to have an efficient header because, you may be trying to move much more than 64 bytes at a time or 64 kilobytes at a time. So you want to make sure that your header is efficient use as well so that you don't end up taking an efficiency hit. And that's what gives us that 93% efficiency. Other questions?
Thank you, Kurtis. It might be available on your website, but I'll read your mind. Could you please touch on some of the key differences from 2 to 3?
Sure. So 2 to 3, we're looking at that right now. So I'll start with that. But one of the big differences here, we're at 200 gig. And as we move over to 3, we will be stepping up to a faster speed. We believe that'll be 400 gig or faster. For that link speed. And we're working with some of the other industry groups that have been put together. OCI MAS just got formed, or MSA just got formed. So we're looking into what they're doing. There's a couple other MSAs that also got formed that we'll be following to see what's going on. Plus, there's work in IEEE and the OIF group. So we're looking at what they're doing, but I think they're going to be a little slower to the table than what we need to do to keep up with the industry leaders.
And as different accelerators evolve and they adopt UALink, do you think there might be need for going higher than by-4 connectivity moving forward?
It certainly could be. So as you look at this, it's of course a moment in time, so it gives you 800 gigabit per second at 200 gig. As we go down to 3.0, that's, 4 ports will give you 1.6 terabits per second. Is that enough? If it's not, you can start to aggregate ports, and that would give you more data. But if you kind of look at this slide here, right, I've got multiple connections. So if I've got 128 switches, I've got 128 ports. So my first packet might go from this accelerator to the one on the far end, and it'll use this first link. The next one would go and use the second link, go through the second switch, still going to that far end packet. So there's a lot of bandwidth, because that's what's important for the training and for inference, by using the solution you see here.
Fantastic. I think that brings us to a close. So thank you so much, Kurtis, for sharing. That was fantastic.